So good morning friends. A lot of queries come to us about the design process that goes into the springs. It's not just the stresses and the number of coils in the dia that you finally calculate. It's the complete process that goes into it, starting from the very basic, the weight of the vehicle, then all the dimensions come into it, the track, the wheelbase, road axis, the road center heights, everything goes into it. So today we are going to take an overview of this design process. I'll start with just a summary of that, what we are going to look into it, so you can understand, have an idea as we proceed. It may be new to you. There are a lot of materials, books present for this. You can take references from there. We are just doing our bit to help you grasp the things better. Okay, so we'll start with the spring rates. The spring rate is expressed in pounds per inch, and it is the pounds per inch. Okay, and it is the vertical displacement of the spring per unit vertical force. Okay, so this is the only parameter that in which we define the stiffness of the spring. Okay, next is the tyre rate. Okay, tyre rate is the vertical force per unit vertical displacement per unit vertical force measured at the ground contact point of the tire. Okay, so why I'm telling you all this is because finally these things are going to help us in the designing of the springs. Okay, so we'll be just taking an overview of this. So after the tyre rate, we go into the ride rates. Ride rates is the vertical force per unit vertical displacement of the tire at the center of the tire spindle, which is measured relative to the chassis. Okay, so this is actually the travel that you are experiencing, the force that is causing that travel, that is called the ride rate. Okay, so when we are going to the calculations of the springs, first we assume a particular value for the roll rates. Generally this is done through your experience. Okay, but the starting of this is done through the experience. There is not a set of defined parameters that do this, or formulas that this is your roll rates. Okay, so when we go into the designing for the spring, we start with we give a guess of the parameters that we need, means of the roll rate. Okay, so it may be tough for you. Even when we did for the first time in BAJA, we didn't have the references from Millikan or other books, Tune to Win, anything. We just knew the definitions we found from internet. Okay, so when we were doing this, we started by we were sitting. These are the forces on our wheels. How much will the wheel move? Okay, how much is the roll? But just taking a feel for the parameters. What is the roll that we require? Okay, and at that point, we struck a value, a sort of value. This much force per inch will help us. So for your FSAE calculations and everything, what you require is a roll gradient of around 0.15 degrees per G. Okay, so this will be, as you lower the values, this will be very good. Okay, so to attain such a value, okay, we require very high roll rates. Initially, this is an iterative process. Okay, so initially when we begin, take some value. Okay, it should be a real value that you can properly use. Okay, so for example, I go in with roll rate of 50,000 pound-feet per G. Okay, so this is a particular value that that I've assumed for the roll rates. Okay, so, and this is for the front. For the rear, I'll go for 30,000 pound feet per g. Okay, because this is a moment that is suggesting body roll per unit the degrees of body roll. Okay, so this for the first step I've started by assuming this roll rate. Now I'll go to tyre rates. Fine. Now some of the books will say you that assume a tyre rate. It is generally for the slick tires, it's around 2000 pounds per inch. Okay, but what I'll suggest you is, like, we are also dealers of A1 tires, Cooper tires from UK. So this particular value is given to you in tire data. Take it from there. For a particular load range in camber and everything, this value is given to you. Take it from there. Okay, go for the rear values and then proceed. So I'll take this around 2000 pound per inch. Okay, now these are the most important values that I need at the moment. Okay, if a close guess of this is made, it is very helpful for us. After this, we won't go into very detailed calculations. I'll just give you the process that we go through, the formulas. Okay, and if you are in doubt or if you need further explanation for that, you can mail to us. We'll give you the complete explanation for that. Okay, if any case of doubt. So kindly remember these values. I'll just state them later. So now let's go into the vehicle parameters that you need. Okay, first what you need is weight static, okay, on each wheel of your vehicle. Fine. You got to measure everything, the engines, the chassis, all the small components, and then write down the weights on each tires. Okay, for this basically you need the CG location. Fine. Second, what we need are the dimensions. There are quite a few dimensions in this. Okay, first is your track, lateral distance between the center of the two wheels. Fine. Next, what we need is CG height from the ground. There is not a particular method for this, but a general method is you put your car on weighing scales. Okay, raise it one by inch from the rear, see the load transfer on your front wheels, and then just there are equations there. Okay, just calculate your weight transfer on the front wheels. You have the CG location. Okay, you have to take some moments and everything. You can get the CG height from there. Next, what you require is your height of front and rear roll centers from ground. So the front and rear roll centers, for this first you need to go into the suspension geometry. You got to be ready with that. Then okay, you can proceed with the spring rates. Okay, so next what we need is CG to roll axis height, or you can say distance. So now if this is my front wheel, this is my rear wheel, this is my chassis, okay, in the side view. If this is this is my CG, okay, and this is my roll axis. Okay, so you got to calculate the perpendicular distance between the CG and the roll axis. I'll magnify this. This is my roll axis, this is my CG. So this vertical distance, you got to find this. This, say it's your h. So you got to measure this distance. On your CAD you can easily do this. So after you're ready with your weight, your dimensions, next what we do is we go for the weight transfer. Assume a particular value of G, lateral force, that you are trying to take, coordinating situation. You when you are making a vehicle model, you can do this for a number of G's of coordinating forces that you experience. But here I'll just take example for a single 1 G of cornering. Okay, so suppose we are taking load transfer at 1 G, pure lateral. Okay, there is no acceleration of the car, so we are not assuming here that we are not going for longitudinal load transfer. Okay, so at 1 G, what I require is weight delta W. 1 G, taking the front axle. Now the load change that will be experienced is weight of outer tire minus weight of the inner tire. Get this value. Okay, then we require delta on the rear. Okay, get this value. Next what we require is we need to find the ride rates. Okay, ride rates I've initially explained. So ride rates is basically load change divided by the ride travel that you require, your specified ride travel. Okay, so in Formula cars, for your Formula and BAJA, FSAE in BAJA, we require generally in Formula car around 2 inches of travel, or you can go for 1 inch also, and for BAJA we require 10 inches to 15 inches. So the particular point here is you don't require your suspension arms to hit the bump stops in your complete range of travel. You want to attain this amount of load change within your specified travel or within your 1 inch of travel. Okay, and you want to leave around 0.5 inches to 0.25 inches for the bumps and load and the travel of the suspension because of load transfer happening from the longitudinal accelerations or braking. So we need to cater for all that. Okay, so we go here for the ride rate. You can get your ride rates from here, both front and rear. Fine. So after we have decided our ride rates, what we need to do is we need to find the front and rear ride frequencies. Okay, so for the front frequency we have I'm basically referring to Millikan here, so in case of doubt you can refer to the formulas there or mail to us. Fine. We have ride rate front into 12 into 32.2. This is to convert, because we are in Millikan and generally we also take our data in pounds per inch. So this factor is to convert the G in pounds. Okay, so upon W. So this W, okay, 1 and 2, so 1, this W is your static weight on the front tires or the rear tire, if your calculation is for rear. Okay, so when I find this frequency WF and WR, fine, what I have to see is, because in Formula cars our main aim is neutral steer, you must be knowing neutral over and under steers. We require neutral steer. As we turn the car follows it. There is no side stiffness gain or anything, just the car has to follow. Fine. So to cater for the neutral steer requirements, what we require is, for the mid-engined cars, omega front should be greater than omega rear. Okay, and at if this point, if your omega front is coming less than omega rear, you have to change your ride rates and the roll rate values that we have assumed at the start point. This is a iterative process. So again, you have to change those values, come back to this till you attain this front omega greater than the rear ride frequencies. Okay, so now assuming that you have got this, front is more than the rear, we go in now into taking out the roll gradient. Okay, whatever roll rates that we have assumed are doing at this point. So if for a particular G, like 1G we are taking, what is the amount of roll that we are experiencing? Okay, so we don't want much roll because the steering response is suddenly gone. We have experienced that. Okay, so we don't want any roll in cornering. So we'll go for, find that here, to AY is equal to minus W into H divided by the sum of the front and the rear roll rates. Okay, your W here is your static weight of the vehicle, or the static weight of the vehicle. H is your CG to, I've explained it, CG to roll axis perpendicular distance. Okay, these two are your roll rates. Front and rear. So by this calculation, you know exactly the assumptions that you have made of the roll and ride rates, how much your car is rolling. So you can get a feel of what your steering is doing, means is the driver able to control it or not, the response of the vehicle. You can get a feel of it from here. Okay, so what we do at this point is, we have the ride rates, we have the roll rates, we have the tire rate, explained to it when we started. So now we need to transfer all these rates to the wheel center. Okay, so wheel center, this is again a different rate. This is called the wheel center rate. So this has got a typical definition that I've written it for you because I couldn't remember it. So this is actually vertical force per unit vertical displacement at the location along the spindle corresponding to the wheel center line measured relative to the chassis. So basically what we are doing is, we are transferring this force we are calculating at the wheel center. So our springs means the force between the wheel center and the chassis. This is what your wheel center rate is. Fine. So let's write it KW. So with the wheel center rates, we go into the spring rate after calculation of this wheel center rate. So the equation for the wheel center rate is KR KT. Let's do it for the rear. Okay, into KR T minus KR. This is your rear ride rate if you are doing for the rear, and this is your tire rate rear, assuming that you are using all four are your same tires, but the weight difference may change the tire rate. Okay, now we have the KWR. Okay, so when we have the wheel center rates, okay, how this is modified is, because of your installation ratios. You know about the installation ratios. I know you may be having the example. Installation ratio is the, suppose this is your tire, this is your upright, these are your wishbones, this is your spring to the chassis. Okay, so now this is our chassis. Fine, these are chassis pickup points. Let's say this distance is A, this distance is B. So now our installation ratio is equal to A by B. So whatever this comes out to be 0.5, its maximum value is 1. So everything is less than 1, 0.5, 0.8. So as it decreases 0.5, 0.4, the more stiffness you are getting at the spring, the less stiffness you are getting at the spring. Okay, so this is a very good parameter to attain whatever stiffness we want from the spring. It can be used to modify these things. So now we have taken out the wheel center rates. KW is equal to KS into IR square. We all know these things. Okay, you're doing FSAE BAJA, you know this. Okay, so here KS is our spring rate. All the hard work, that all the iterations, all your hours, everything, the sweat is for this term. So this KS is going to decide what our car does when we race. So all this is for this. Okay, so now this spring rate, okay, KS, so we have taken out the value of the spring rate here, okay, magnitude. Now what we want is to find out the number of coils, the coil diameter, wire diameter of the spring, to attain this KS. Okay, so for this, in Millikan you have the equations there. We have KS is, G, your modulus of d to power 4 upon 8d cube into n. Fine. Here your d is wire dia of the spring wire. Okay, d is mean diameter of the spring. So this particular, if you see the top of the spring, this dia, this is your d. Okay, so now n is number of active coils. So when you see a spring, you'll see half of the coil at the bottom seat, half at the top seat. We don't include those. Okay, the complete coils at the center, those are your active coils. Okay, so from here KS, the spring rate, you can find out your number of active coils. Now you will say that we have two other variables, D and D. So what happens is, when we go into the formula for maximum stress that our spring can take, we have F is 8d into W upon pi d cube. This is the static weight on the spring. Okay, so this F, this is our uncorrected stress. Okay, this is the maximum stress that is coming on the spring. Okay, so if we design our spring with this stress, it's going to sag in the service. Okay, so now what we want is to increase this. So there is a factor called wall factor. wall factor. So what this does is, this is inversely proportional, and I'll not quote the equation for this because we'll have copyright issues and lot of things. So when this is proportional to the ratio d by d. Okay, so if our d by d is 5, the wall factor comes out to be 1.1. Okay, so now see, we have a very big ratio here, d by d, but our wall factor is increasing by only 10%. So what is that this does mean is, we multiply the f into the wall factor. This is our final stress that we'll design the spring for. Okay, so now we have the stress value, we have the mean dia, we have the number of active coils, the wire diameter. Okay, this parameter is listed in, you'll see that in FSAE, in the SAE guidelines, this there is listed with the stress values that the wire can take. So this, for your stress value, you can find this D from that table. Okay, so in this way, finally we have the number of active coils, wire dia, and the mean dia of the spring. So with this, now your spring is completely ready. You can go to manufacturer and start racing. For any doubts, any kind of explanations, kindly mail to us at tinsiracecars@gmail.com. Thank you very much. Have a great racing season ahead. Thank you so much.